Good morning. Welcome back to our Let's Talk Science session. Today's topic will be implementing AI models sustainably. And what is the background of this session today? There are various applications that are applicable for AI, as we know, like predictive maintenance or process monitoring. And the AI models are trained by large amounts of data needed, but the question comes up, how long are these models predicting and the predictions are valid that we can expect? This will be discussed in today's sessions. In addition, Professor Metternich and Mr. Jordan will reflect on the involvement of employees to gain confidence and trust in the predictions of the AI models on the machine of the process. Professor Metternich is head of the Institute of Production Management at the PTW Institute in Darmstadt. And Mr. Jordan is research assistant at the same institute and is working on the conduction research on reliable use of machine learning algorithms in production. So, Mr. Metternich and Mr. Jordan, the floor is yours.
Thank you. Many thanks, Dr. Schäfer, for this kind introduction. Well, as you already said, we will deal in today's session with the question how you can implement or how you can run an already implemented machine learning model over time, because we found out that the performance will degrade over time of a once trained machine learning model. And the question we will deal with is, why is it so? How can you detect that a machine learning model is not as performant as it has been when you once trained it? And what can you do to address this? And as you said, it's all about trust into the predictions of such a machine learning model. So this is the agenda for today's webinar. And before I hand over to the deep expert in machine learning, Nicholas Jordan, I will give an introduction into this topic. And here we have some results of surveys that I would like to share with you. On the left side, you see companies responding to the question, what is the significance of machine learning models in your company? And interesting is that today, many companies just see a medium or low or very low importance. But in 10 years, we see that there is a high to very high importance of machine learning models. What does it mean? It means more or less that today you can make a difference if you apply machine learning in your own processes or in your products. It's something that others will not have probably, and you have an advantage in competition. But in future, this is in 10 years, it's mandatory. It's something that your customers will expect from you and the services that are based on machine learning. On the right side, you can see this is from our own survey, from an architect survey of last year. You can see that unfortunately, well, only 40%, that's what you don't see here, but only 40% of small, medium-sized companies have today applications of machine learning. But then if they have it, it's just about 25% who have it, which have it in operation. The other 75% is just they have a concept or they have a proof of concept, but only 25% of the applications are really in operation. And the question is, of course, why is it so? And we try to find that out. And here you see answers to this question, why do you just have concepts or you're just running proof of concept? And here are the opportunities, or let's say problems and opportunities that have to be addressed. And the practitioners, they tell us it's especially the time dependency and seasonality of data distributions that might change over time. It's the required quantity and diversity of the training data that you have to acquire from the process to train a model. And it's also the data quality that is very difficult to assess and then to improve by data preparation. On the right side, you see scalability of models to other machines. When you once trained a model to one machine and you deliver this machine to your customer, then what about the next machine? Will this model fit to this machine? Or what about other types of machines? And can you transfer a model to those machines? And that's not an easy task. And then, of course, it's the labor-intensive update of models, missing standards of automation. More or less, this is about the foundation of data acquisition and having the right sensors and so on. Well, we will deal today with the first two. It's the time dependency and the scalability of the models. And first, how you can understand that a data distribution for which you once trained the model has changed, or how you can transfer a model to a different process in the future. And we will use for this session here, we will orientate on this CRISP-DM and DMME process. And you see here the Biden process. It's not the CRISP-DM process, is just the gray arrows, these big arrows, and it's enhanced by the DMME process, and this is for engineering applications. So it's the cross-industry standard for data mining, and it's together with the engineering applications, because in engineering we have sometimes different necessary things to do than we have it in just artificial intelligence applications. And so first we need to build also, before we have the business understanding, we need to have the technical understanding of the process that we look at. We need to technically realize and implement things, data understanding, then data preparation. We then build the model, we evaluate if the model is doing the right thing, if it's performant or not. Then the technical implementation again within the machine, and then we run the process and deploy this. And that's the CRISP-DM, process. And we will look here at an example that is, well, hopefully familiar to you. This is a machining process, and we use the data we get from this process to predict the quality of the machined part. And this is a data set that is available for the public, made by Bosch. So Bosch has been producing parts for several years even, and they produce a data set. And with this data set, people like Mr. Jordan and other scientists, they can work and find out how performant an ML model, for example, is. Okay, so let's go into this here. First, business understanding. Business understanding means we want to predict the quality of this part without taking it off the machine and put it in the measurement room, and it takes time to measure this part. We want, when the process runs, we want to understand, will this be a good part or not? And what can we do, maybe even to change the process, to save the part? We build a technical understanding about the process. We implement sensors, and here you see this sensor. This is the sensor here, and this was implemented in 3 axes. It's an acceleration sensor which gives us the vibrations, and that was adapted to all 3 axes. And then we get a data, well, raw data over the time series of the raw data. They look like this, and that was done for 3 equivalent machines on 15 machining operations and for 2 years of operation. So then you take out the data from the machine, you have these sensors, and you have the data now available, and you have different opportunities to train a machine learning model. You can use the time series as it is, as raw data, to train a model. That's possible. or you transfer it into the frequency area, and you would use a Fourier or a wavelet transformation for that. And the next opportunity would be also to create features from that. That would mean feature. What is a feature? A feature would be we calculate averages, we calculate the skewness of a distribution, and so on. Standard deviation would be, for example, a feature. So all three opportunities you have to analyze this data set with machine learning models that you would train with these data. We will look now at the last opportunity here, this right opportunity we created from this data set that we got from Bosch, and so Jordan did that, these features, and we trained using these features a so-called random forest classificator. And this random forest classificator is able to classify, using these data, to classify the parts into good parts or bad parts. It's simply, you take out the data for a certain part, you label these data, which simply means these data belong to this part, and then you train the model. And then in the future, if you give new data to the model, it should be able to predict if a part is good or bad. And that's done here using a random forest classificator. And then we split up the data into training data and test data. So with the training data that we get from the machine and from the measurement of the parts, we can train the model. And then we use a split of the data, which are test data, to find out if the model really does what it should do, which is classify the parts with a good performance. And this is measured by a so-called F1 score. We don't need to go too deep here into the F1 score, but it's a measure that is consisting of the accuracy of a model and the recall. And it combines both indicators, and it combines the advantages of those both indicators. And what's interesting now is we get, when we test this trained model with the data from the same time when we did the training, we get an 84% F1 score, which is quite good. It's really good, because looking at the precision and recall that are part of the F1 score, we are almost here at a precision of 100%. That means all the predictions are almost 100% accurate, and that is a really good result here. And also from all predicted good parts, we almost recognize 75%. So this is the performance for the first year. But then if we take the data of the second year and use these data of the second year with the model that was trained with data from the first year of operation, then the picture is different. The precision goes down dramatically, and recall also. And so the F1 score is also dramatically reduced. So this is a very good example that shows how the performance of such a once trained model is degrading over time. And you can very well understand why, because there is wear in the process, for example. Maybe the parts change, the material changes that you machine in this process. So we have a time variant behavior of the process, which then does not allow the model to be as good as before when the process was a different process. So we have over time a change in the process due to wear and other circumstances, and the model cannot be as performant as before. And now I hand over to Mr. Jordan, and he will explain to you how we can recognize this.
Yes, thank you, Professor Metternich. What we want to emphasize also about this example is that it's not obvious to the user that this performance degradation has taken place. So we see now that the performance was worse in the second year, but you would only notice this if you would explicitly test for it, because there's no kind of standard way for the model to tell you, hey, there were some changes in the process, I need to be retrained. And kind of detecting this problem that we need to maintain our machine learning model will be the major subject of the talk today. But first, let's look a little bit deeper into the reasons that Professor Metternich also mentioned already, why this actually happens. So why does our machine learning model performance decline over time, and why doesn't it just stay at the level that we have seen before? And of course, one of the reasons is that the model environment, which is the kind of shop floor, is dynamic. So you have several factors that are changing over time. One very obvious one is, of course, the tools and the machines where you will exchange the tools. You will have overhauls of the machine parts, which may change their characteristics, especially when we are talking about kind of frequency responses for accelerometers. You may have other product variants or other materials that you get from a supplier. There might be changes on the shop floor layout where there's now a different machine standing close by that is also generating vibrations. You might have other employees that set up the machines differently. Or, of course, there could be data and network problems when the sensor is drifting, or possibly also when you have some text input from your employees and they just put in the data sometimes differently. And all these kind of factors contribute to an error of the model. And what other factors kind of contribute to the error of the model, I want to now talk a little bit about. So in total, there are kind of 3 components from literature that make up this error of machine learning models. The first one is the model fit. So we have seen before, kind of in the beginning, we had an accuracy of 84% or an F1 score of 84%, which is already not completely perfect. It's can be acceptable for the business case, but there's of course kind of an error already existing in the beginning. Then in addition, we might have data quality problems. So for example, if a sensor might drift, or if you have kind of problems in your transmissions of the sensors, if they work wirelessly, for example, you might have missing data, which contribute to a possible error of your machine learning system. And lastly, there might be a scope compliance, which is actually the majority of the reasons on the left side. So this means that the environment that we are now using the machine learning model differs from the environment where we once recorded the training data. So in the example of the milling machine, this could mean we had 1 year where we recorded the training data, we trained our model, and then when we use the model in production, the certain things that I explained on the left side change, which kind of changes our data distributions. And as I said, this model error is not always directly obvious because there's no way for you to tell if my machine learning model is now good or bad if you don't explicitly test for this. And kind of getting this or estimating this model error is really important for a number of things. First of all, it's important for acceptance with the employees. Of course, if a system, especially a black box system like a machine learning algorithm, if it doesn't behave as you would expect or as you were told it would behave, you could lose acceptance for using the system at all. Secondly, it might be important for safety reasons. If we think about a machine that maybe is controlled by a machine learning algorithm that controls certain operations, it can be safety relevant if this algorithm is not working as expected. And lastly, of course, it's important for economic viability, both from the side of the machine learning implementation itself, because there's usually a large investment involved to set this up, so you want to actually use it for a longer time, and also from the safety point of view with the production machines that are involved and could take problems from this. So this model monitoring is very important, and we now want to look at how this can be done. And first, I want to talk a little bit about how this can be done from a project management side. So Professor Metternich already introduced the CRISP-BM model, and the CRISP-BM model was introduced over 20 years ago, and recently there has been kind of a successor model introduced called the CRISP-ML process. And this was introduced only last year by Mercedes-Benz Research, that with findings that they kind of made in their own machine learning applications. And this CRISP-ML process model introduced several changes to CRISP-BM, and I don't want to get into all of these, but I want to get into one really important one, which is that we now have a monitoring and maintenance phase in the end. So the project management of the CRISP-VM process kind of ends after the deployment. So when you set up your machine learning model, the process is kind of finished. But in this CRISP-ML process, you have one ongoing kind of step, that is the monitoring and maintenance, which really focuses on monitoring the machine learning model and possibly maintaining it. So just to visualize this, the problem that we have seen in the example is that if we have a static model, the performance may degrade over time. So it will get lower than we have seen on some test data that we have provided in the beginning. While the goal of this CRISP-ML cycle, or specifically the last step, is that we first kind of notice that the performance is degrading, and then take certain steps to bring the performance back to the original level. And how can this be done from a system architecture kind of point of view? So here we see just a schematic visualization of a generic machine learning use case. This can, for example, be the example that Professor Metternich talked about, where we have a production machine and sensors. In this case, it's accelerometers that gives us frequencies and amplitudes as a data that is consumed by our machine learning model. Our machine learning model then in turn generates predictions. In this case, it was if the produced part is good or bad. So if we need an additional manual quality check or not. And these predictions are then kind of consumed or used by the machine operators to decide, as I said, if there might be another quality check necessary. And now we want to implement this data and model monitoring and model maintenance. And for this, we have actually several clues or inputs that we can use to check if our model is still performing correctly. One thing that I want to talk about and later show an example is external or manual triggers. So of course, if there was a major product variant change, or if there was a major machine overhaul, we know that probably our machine learning model will not behave as it previously did, because it doesn't know this new parts or this new product variants. So this is a really easy method of monitoring this. If this is not possible, or if there are changes that we cannot notice in this way, we can also look at the data distribution to for example, detect drifting sensors. We can further also look at the predictions and see if our model gets less confident over time. And lastly, we can use our machine operators to get feedback on the predictions. So if we notice that for a lot of the parts, for example, where we detected a quality problem using our machine learning model and they were actually okay, of course, we can use this feedback to kind of say our model needs some maintenance. And this is done with the ultimate goal of then providing a model update, so our machine learning application works continuously and reliably. So I want to dive a little bit deeper into how this data and model monitoring can be done. So how can we actually notice that our model is not performing well anymore? And this can be done in several different ways. First, it can be done in a supervised way where we have actually the prediction feedback available. So in the use case that we talked about previously, this would mean that we have for each part where we detect the quality or predict the quality, some feedback if this prediction was correct or not. But usually this feedback is not available because in a quality prediction use case, we want to use our machine learning model to predict the quality, so we don't have to measure it in the end. So we usually don't have this feedback. But there are other use cases where we actually do have it. So for example, in forecasting applications like energy demand forecasting, which is a very relevant topic in energy research nowadays, we will at some point know if our prediction was correct because we have a certain forecasting horizon. And as soon as this forecasting horizon is reached, we can actually just check if our prediction was comparable or close to the real value, and then kind of monitor this error rate over time and see if our model performs worse over time. But as I said, in most use cases on the shop floor, this is actually not available because we use the machine learning model to actually don't have to do the manual checks anymore. So in condition monitoring or quality prediction, we usually don't have always this feedback. Here we have several other ways that we can employ. One is external triggers, as I already introduced and will soon show an example. The second is monitoring of input data. So we can monitor if our input data distribution changes over time to detect things like sensor drift or missing data. And lastly, we can monitor the model confidence or certainty over time, which I will also shortly talk about. But this is still kind of abstract, so I want to show you some examples of how we did this in research projects. So let me start with the external triggers. Here, I want to go over a project that we did together with a large chemical company in Germany. And this chemical company is producing pigments, and these pigments, they are used in car paint, they are used, for example, in food coloring. And one of the last production steps in the production of these pigments is a filtering step. And the pigment, it goes through machines that look kind of like this, where the pigment comes in from the top, and then there's a filter in the middle that looks kind of like this, and the material then flows to the bottom, and usually it is then already packaged. And as this production step is then the last one actually in the production of these pigments, it has enormous influence on the resulting product quality, because yeah, it's the last step in its production. And these filter sieves, as you see here on the white side, they have this block attached to it, and this is an ultrasonic generator. So there's an ultrasonic vibration that is applied to this sieving machine to make the material flow through the pores of the sieve that you can exemplary see here. And this company has a problem, which is that at some point these sieves often show tears. So there will be certain rips existing in these sieves, and then the material can actually flow through it unobstructedly. So there will be then impurities in the end product, and the end product has to be reworked, or it has to go to waste in the case of food products, for example. This is even made more difficult because these tears kind of come abruptly. So there's no way to anticipate how long it will take, if it will take 1 hour or 1 week until a tear will start to show. And usually this is at the moment solved by manual checks by technicians. So there will be actually a technician that stops the process, takes a look into the machine, and checks if these tears are existing or not. And our idea in this project was that we use accelerometers that are attached to the outside of the machine to check if the frequency response of these machines change, because they get these ultrasonic vibration, and we expect that the response from the machine will change if there are some holes in the sieve in the machine, and the material can flow through unobstructedly. So I want to show you how our kind of experiments look like, and here I show you an experiment where we had a sieving machine where we at some point introduced an artificial hole into the surface to kind of check how our frequencies change. And what you see here are 2 different sensors that are mounted on the machine, and on the x-axis you see the time, and on the y-axis you see the frequency. And in a light color you see kind of a high amplitude for the frequency area where we are at the moment. And at some point where we have the red arrows here, we introduced a hole into the sieve, and you can actually with your own eyes or with your bare eyes see that there's then a change in the frequency response, especially in the areas where the ultrasonic vibrator is vibrating, which is kind of these 2 areas here. And so far so good. So we concluded, okay, we can use machine learning or an anomaly detection model on this kind of data from our accelerometers that we attached to detect these problems. But when we then made more and more production runs, which I have an example for here, we saw that the frequency response looks very different each time we tried it. So here, for example, you see a second trial that we did after the production batch was changed. And you see that still on one of the sensors, the artificial tear that we introduced again was visible again with your bare eyes, but the frequency response, both for the sieve that is actually working and for the one that has a problem, look very different to the one that we saw in the first trial. And this can be for a multitude of reasons. One of the reasons is that when the batch is changed, the sieve is kind of assembled in a little bit of a different position, which also changes the position of our sensors. And therefore the sensor output looks a little bit different. And this now poses a problem if we have a machine learning model that we train on a data set that might look like this, and then use it on something like this. It will give us a lot of false positive anomaly detections because all the data now looks very different. So we need some kind of strategy to update our machine learning model over time, and also if these batch changes occur. And I want to tell you now how we are doing this in the specific use case. So here I have a schematic where we again see the time and production, and on the top we see the process state. And this process state just means if the production flow in this sieving machine is at the moment running or not. So at some point it will start, the batch is produced, which usually takes a day or maybe several days, and then the batch is changed, another product variant is produced. And how we now do the machine learning model operation is that we first record a data set in the first few hours, because here in the first few hours of operation, we know that there will not be a hole in the sieve, because before the start of production, the sieve was manually looked at by a technician. So we are actually sure that there's no problem at the moment. Once we have recorded this data set, we train and deploy a machine learning model that is then used in the time ahead to detect if there are any problems with these sieves. And because the characteristics of these sieves can slowly change over time, it is necessary that we then record the data further and update our machine learning model over time. So we will actually, while we are monitoring if there's any problem, still record the data and then train another machine learning model that replaces the first one, which is then trained on the most current kind of response from the sieve where we know it's in an okay state. And we repeat this kind of continuously until there's a change of batch. So then, of course, the data is more or less thrown away because we don't need it anymore. We know that now the data will look very different. So if there's a change of batch, a new data set will be recorded and then a new machine learning model will be trained. And in this way, this research project is still ongoing, but we are in this way reliably capable of detecting these sieve tears, even if the characteristics of our sensors change over time. And for this, we use a fast anomaly detection algorithm called the histogram-based outlier score, which basically just compares the statistics of the data that we record with the data that we see at the moment to see if there might be a problem with the sieve or not. And in this use case, it's very important that we have a machine learning model that is easy to retrain, because as you see, we retrain it every few hours. And then we cannot use a large neural network, for example, that takes maybe a whole day to retrain. So we use a simple algorithm here that we can retrain multiple times a day and then always adjust to the project condition.
And I have to add, this retraining is done automatically through a pipeline that you already programmed. So that's
exactly,
not work for someone who does this again and again.
Exactly. So the data is recorded. It is stored automatically in a database, and there are automatic triggers that will then train a machine learning model and put it into the server where our anomaly detection application is running without any interference from an employee, because this is kind of fully automated. So we have now seen an example for how we can use periodic retraining or external triggers to see if our model is still up to date and how we can update it in this way. But as I said before, this is not possible in all ways, because when we have a use case that is similar to the one Professor Metternich introduced about the quality prediction on the milling process, this might not be possible, because we cannot retrain a model every 3 hours because we don't have any new data then after three hours. We would have to generate a new data set where employees measure every part that tells us if it was actually okay or bad, and then we can retrain our model, which of course is not possible to do every few hours, because this would make kind of the use of the machine learning model itself absurd. But still, there are several ways that we can employ to check if our data distribution changed without explicitly testing for it. And I want to now show one way how we did this in this data set that we introduced before. It is now the use case again that Professor Metternich introduced, and in this use case we have seen that the performance of our model declined sharply in the second year. So as we've introduced before, we had kind of a good performance in the beginning of the training, but then when we tested the model in the second year, the performance declined relatively sharply. So the question is now, how could we check if this is happening without explicitly testing for it? And one method of doing this is to use a reconstruction error of input features to detect, for example, if there's a sensor drift present or if the data changed significantly. And this reconstruction error is calculated using an algorithm called the principal component analysis, which is a linear transformation used for dimensionality reduction. And maybe some of you already know this algorithm, but I prepared kind of a short visualization on how this is done. So we have first our input data that we get from our sensors during training. So we are now talking about the first year that we use as the training data set. And we compress this information then to a state of reduced dimensionality. using the principal component analysis. And after this step, we reconstruct it again to the original state. And why do we actually do this? So why do we want to reconstruct the input again? The goal is now that if we have data that looks a little bit different, like maybe from the second year, our reconstruction will not work so well anymore, because we trained it on the first year, where we also trained our machine learning model. And this means it has kind of learned the characteristics of our data that it looks like in a nominal state. So if we will try it on data where the sensors have drifted or the distributions look different, the reconstruction will look a little bit worse. And we can then compare these reconstructions and calculate an error of how this data has changed. And if we plot this error over time, which we have done below here for the data set that we have talked about so far, we can actually see that in the second year, the reconstruction error rises sharply. And this is also the assumption of this method, is that the reconstruction error will rise if the data distributions changed. And this is a very important information for us because we can now see, okay, our data distributions have changed. We should check if our machine learning model is still reliable. And we did this without actually measuring a single part, just by looking at the input data that we get from our accelerometers. And yeah, this gives us a method of really checking if our model is still working reliably when we don't have prediction feedback available. Lastly, I talked now a lot about the data and model monitoring, how we can actually see if our model is working reliably or not. I want to spend the last slide from my side on the model maintenance. So what do we actually do if we detected that our model is not working reliably and we have to update it? And I want to talk about this only high level because we can fill another webinar, or actually several webinars with this. But there are two kind of major options. So one is the retraining. We have seen this before on the example of the chemical process. So here we just collect new training data. We possibly merge it with existing data sets that we already have sampled in the history, and then train a completely new machine learning model. And in a lot of use cases, this is actually fine. If the machine learning model is not too complicated, it doesn't take a long time to train, and we have this data available, we can do this, and we should also do this, because it's the most simple and reliable method. In research, we are more and more looking into methods of transfer learning, where we kind of try to not each time completely train a new model, but to transfer existing models to new tasks or environments. So to adapt models that have been trained before, for example, to a changed time difference, as we see in the milling data set. And this is especially useful for models like neural networks that take a long time to train, and we cannot retrain every few hours. And this concludes my part of the talk, and then I would give back to you for the main takeaways.
Danke, Herr Jorgen. Thanks a lot. Yeah, so let's conclude our talk here with the key findings that you should take with you from this webinar. So I hope you could take away from our presentation that machine learning models that have once been trained decline in performance over time for different reasons, and you need to be aware of this. So you need to have also a model maintenance, if you like. So for long-term use, you have to monitor then your machine learning model and try to understand, is it still as performant as it has been when you introduced it? And for that, Mr. Jordan, he has shown you some ways how to detect this if there is a change in performance of a machine learning model. And you can detect this just by looking at, well, you simply can detect it by looking at the input data stream. If the characteristics of this input data stream has changed, like the distribution has changed in terms of average or standard deviation or whatever, then you already know there is something wrong probably, and the model will be not as good as before. And you can also look at the model predictions over time and compare the model prediction with the reality. And if you see that the prediction doesn't comply with the reality, then you also have a good sign that you have to retrain and maintain here your model. So this is the end of our presentation here, and as I understood, we still have time for questions and discussion. So thanks for your attention from the two of us, and we are looking forward to your questions.
Yes.
Well, thank you very much, Professor Metternich, Mr. Jordan. This was very interesting and also very understandable due to the practical use cases you have shown. Maybe some questions here. First of all, the Bosch use case. This is a large workpiece, so I was astonished. They received data for 2 years. But looking into it more in depth means that if you have work pieces like this, you need quite some time to get enough data to build up a model, because one workpiece is one set of data, and you need, I don't know, how many work pieces do you need in such a use case in production?
Yeah, this is a very good question. So there are two parts, I think, to the answer. So first of all, the image that we showed when we showed the Bosch data set was kind of an example image. So this was not the actual workpiece that was machined for the data, because the actual workpiece and the process information was confidential. But okay. It's still a relevant question. We have another research project at the moment going on at the Institute, where we work together with, it's a European project, and there we work together with aerospace manufacturers. So companies that build parts of turbines that work in airplanes, for example. And they have this exact situation, that they have pieces that are in a CNC process for a really long time. And they're actually, this process monitoring, if there are actual problems occurring or not, is very valuable to them if you can do this with machine learning, because these parts are in a CNC machine for a long time. If you process them for several hours and then notice there has been a problem early on, then this whole process goes to waste, and they have a lot of kind of financial damage that is possible if they don't notice these defects. And for them, we also built an algorithm that detects deviations from the process state early on. And depending on the complexity of the process, not a lot of parts are actually needed for this. So in this use case, we trained an algorithm using, I think, several dozen to 100 parts, and it's working reliably. It always depends kind of on the use case and how complex the machine learning, the machining operations are.
Okay, thank you. As you mentioned, it is a challenge if you have, for example, totally the same process, and for whatever reasons, maybe there's a machine breakdown and you put the same process on the same kind of machine, but it's a different machine. Then the machine has different dampings and different characteristics, dynamics and so on. Is there a possibility to very fast adapt the existing model to the new circumstances?
Yes, this is a very interesting question, and also a very relevant question, and something that we and also the people that are doing research in kind of the core machine learning topics are looking into a lot. So there are several ways to adapt models, but they're all still kind of from the research point of view. So there's a big kind of topic of research at the moment that is called domain adaptation, where really the goal is exactly what you have described, where we have a machine learning model that is trained on one machine. We, for example, want to use it on a different machine, and how can we adapt this? And this is an interesting field of research. There's, for example, one approach which is called unsupervised domain adaptation, where we take data from the new machine, but in the case of the quality prediction, for example, only take some data where we don't know the labels from. So we just record data from the new machine for a few hours without making specific experiments, and then try to adapt our model using the statistics that we see on this new data set and the statistics from our original machine. And in some use cases, this works well. In other use cases, this doesn't work well yet. It really depends on how large the changes are between, in this case, the processes.
So there's maybe the possibility that you have a, let's say, as the process or one part of the reflection, the process or the machine is the same, and you only change one parameter, like you change the machine, or you change the process because you have a light variation in material, that you have a basic model, and you can describe variations around the model?
Yes, you can do that. Usually it's not done explicitly, so you don't describe kind of to the algorithm that a specific kind of parameter has changed. Usually you record the new data and with specific calculations compare the statistics of this data and try to adapt your model to these new statistics. But in addition to these this domain adaptation research that I talked about, there's also a really interesting field of research that is very popular at the moment, which is physics-informed machine learning, where we use actual simulations or mathematical descriptions of the machining process to inform the model specifically about what's going on in the machine. But this is very early on, and I haven't seen it deployed in practice. But it's for sure a topic of great importance, because it would make the adoption of machine learning in production environments very more efficient.
Mm-hmm. Yeah. One more question. You described the maintenance process in one aspect like principal component analysis. So it's a calculation back and forth, let's say it shortly, you know?
Yes.
Yeah, and is there maybe, from my understanding, also another aspect of triggering, so that you have your sensor which delivers the necessary data for your model, but you have another sensor that shows you the relevant change why the prediction goes bad. Like you measure the temperature of the bearing and you see, there's something changing, and that's why I predict that my model will run out of the characteristic.
Yes, so this principal component analysis method is really only one of kind of a large number of possible methods. And this is especially an interesting method if we have multiple sensors that are streaming and used in our machine learning model. So we have a multivariate input data, and we have a model that processes this multivariate input data. And the principal component analysis allows us to, at the same time, more or less compare all distributions of this data, but you can also do this in a univariate fashion. So there are actually program packages available that are really easy to use, that only compare the statistics of a specific sensor, for example, or a specific input signal, as could be a temperature sensor, and then alert if this specific signal is out of the expected range, for example. So this is definitely also a relevant use case. The principal component analysis has the advantage that it can compare multiple signals at once.
Okay, thank you. I think this was very good information also for people trying to look into this topic for their processes or for their applications. Thank you once again, Professor Metternich and Mr. Jordan. For our users, the next webinar will be end of October, last Wednesday of October, once again with the topic Rethinking Products Thanks to Three-Dimensional Electronics, presented by Mr. Ankenbrand from the Institute of Automation and Production Systems of the University of Erlangen-Nuremberg. So thanks for taking part, thanks for giving the presentation, and I wish everybody a good day. Bye-bye.
Danke. Thank you. Bye.